welcome you to this tutorial. My name is Wilber Ssebuyungo Kivekayunga. I'm a lecturer at Nkumba University. I'm also the managing director of the Action Entrepreneurs and a consultant in there. We do planning, management, education, and consultancy. We also do international developments in digitization and green transition. In this tutorial, we're going to look at quantitative skills, but specifically looking at how we can use SPSS, entering data in SPSS, and also analyzing data in SPSS using regression analysis. So here we go. For you to have SPSS on your computer is very important. So if you have SPSS, you can open it so that we move along. Remember, in our previous tutorial, we saw how to enter data in Excel and also running regression analysis in Excel. So this data that we used while running regression analysis in Excel, as you see the output data here, is the very data we're going to base on to run in SPSS. So this data that has age, pressure, cholesterol, and then risk scores, we are going to use it. So in Excel then, we had our risk scores as our dependent variables, age, pressure, and cholesterol levels as our independent variables. So it is from that data that we are able to run our regression analysis then. Now that you're going to follow up the workings of regression analysis in Excel or your spreadsheet, now we're going to use this very data in SPSS. So your SPSS, when it opens, I want to open my SPSS here, and this is now my SPSS. This SPSS here, when it opens with two views. There's what we call data view and also what we call the variable view. Our biggest concern here and concentration is going to be in the variable view. This variable view was set for you to be able to set up or to make a setting of what you want your data to appear and how you want your data to be. So this setting here of the variable view is where we're going to set our data as we extract it from the spreadsheet or any source that you have or your data collection instruments. So here in our first page, this first row, we are having what we call age. So you can type there. However, the rule for writing in the name row here is that you don't need to space, because spacing will create an error. So what we do, if you wanted to write age group, for example, a word like age group, you'd pair these words and make sure they are like that, age group. Or otherwise, you put a dash in the middle to separate here. However, what you should be knowing is that what you do here in the name column is what appears in the column for age here, for the column for data view there. So we are only setting up here in data view. I've come back to variable view because the variable view is a setting of what your data is going to be in data view. So back to variable view. So we are going to use the only word we are going to use here. For this case, we are going to use the word age. Then we ask ourselves, is this going to be numerical data? Yes, this is going to be numerical data. Of what width? Width here means the number of significant figures or place values that age has. For basing on our data that we have seen before, age has two significant figures or two place values. The maximum here has two significant figures or two place values. So that means that for us here in SPSS, we are going to say age is going to have 0 decimal places, but the length of our numbers, numerals, is 2. Then the data level, we can call this age of respondents. This data label here, it means that these are the names of the of those headings or those figures, and how you want to label the figures, if they are graphs, if they are tables, and or the graphs that you want to run in SPSS. How they will be named will be according to the labels here. Then we're going to have our values, and our values here, in values, if this data had a scale of maybe 0 means yes, there we would say 0 means yes, and then we add that. If 1 means no, then we would add that, so that becomes how our values we are going to have actually labeled. So when we say okay here, that's how even in data view, when you're adding under that column of age, will be having yes or no. But age is not a question of yes or no, so that's why we are leaving values to be none, and missing anything missing in none, nothing will be missing. And then we shall say that the measure will be nominal. We call nominal data as data that is continuous, and maybe responses and data collected from people due to age can vary because of their different ages. So that is continuous data. However, data that is not continuous is called ordinal data, or data that you just label. So say you can call, if somebody says I'm male, you can say yes, number 1 is for male, number 2 is for female. That does not mean that that has any significant meaning in terms of numbers, that you can't have mean for gender. You can't have mean for gender. So that just that labeling will enable you to just be able to manage your data in terms of quantities. But ordinal data is data that is you've just labeled an item a digit, but does not necessarily mean that that digit has significant meaning. So however, if you use a scale here, this scale is good when you're using a Likert scale, or a Likert scale of 1 to 5, of those questions that have this strongly disagree, neutral, agree, and they strongly agree. They are scale questions. However, scale questions can also be from 1 to 2 or 0 to 1, where you say yes means either 1 or no 0 or otherwise. Those are scales of data. That data is called scale. So now that we have already summarized that, we can now copy our data sets here and say we are going to blood pressure. And when we say blood pressure here, that is what is going to happen in our SPSS. So we can come and say here is going to be blood pressure. This here, it is going to be blood. We don't have to space pressure. Then, yes, we're going to name this blood pressure. I've just pasted it there. Host is already there. And blood pressure, we ask ourselves here, according to the data source, and what is the width? Width, it will be 3. So you can see that the digits here are 3. So we shall call our width to be 3. Here, 3. Decimal places, they are none, no decimal place. Then we can also call this one nominal data. Now we are good to go to the other level which we are calling, you can see here, we're calling it cholesterol level. So our cholesterol level here is we are creating here our other column, we're calling it cholesterol. We can just label it to be cholesterol. And then the naming, the label name is cholesterol level measured in magnesium per deciliter. So here, cholesterol is also 3 and decimal places are 0. We remember that we are making our decisions based on this fact that they are 3 digits. You can see here, also there they are 3 digits. Then we go to risk scores. And then when we have our risk scores here, we can say risk score, to be a single word, has 1 digit to 0 decimal place. Now this one is asking us to first label our decimal places, and also here to be able to say 1. Then we can now say risk score, and this is also nominal data. Risk score is nominal data. So now what we have been doing here is to program what should happen in what we call the data view. When we have opened our data view this side, you'll see that what we have had as names here of our data, they are now the column names for each of our fields, data fields here. Now we can go ahead to either type there the digits, or to paste the digits if they are pre-typed. Like mine are here pre-typed. I can copy them. After copying them, we come back and paste these values. Now, after pasting these values, you can see now our data is there. What I'm going to do is to save this file. I save it as, let me save it as SPSS file for hospital data version 1. And let me save it on my computer. So this file has been saved. These are adjustable columns. You can adjust them in the middle. Now we have our data because we have already set it. Maybe someone may ask a question, what if the decimal places, I want the decimal places to be more than 1? If your data has decimal places which are really more than 1, more than 0, we can say, for example, if your risk scores here, okay, if your age was point 1, point 1, point 2, point 3, the decimal place would be 1. So that means that your age here, that will be in 45.0, you will see points. But then you don't want to interpret age in decimal places like that. So what you do is to put it age to be translated into 0 decimal places. On the other side, we can also see that our data has already been displayed, has already been copied and pasted there. So copying it and pasting it there, we have also saved it. Now we can go ahead to run regression analysis. In this session, we are going to look at how to run regression statistics. My name is Ssebuyungo Wilber Kivekayunga. I'm a lecturer at Nkumba University. I'm also the managing director of the Action Entrepreneurs. Meanwhile, you can now log on to our YouTube channel, which is Wilber S. Kivekayunga, and then you'll find many tutorials pertaining to education, business, and management and planning. We also hold trainings in communities and the various countries. We offer consultant services in business and in education as well, including NGOs. You can subscribe by pressing the subscription button. Now we can continue with our SPSS. Now to run regression statistics or regression analysis, we come here in SPSS and click Analyze. You will see a thread of all other alternatives, but what we want is to run regression. To run regression here, now you can click Linear. Regression, go to Linear. We are selecting Linear. Now in Linear here, we are saying let us have our, these are now our, what you had here as your variables. These variables here, we want to interpret one variable to be the dependent variable. So we are saying let all other variables depend on risk scores. So because all other variables are depending on risk scores, so risk scores becomes our dependent variable. And the other three, they now become our independent variables. So you highlight them by clicking one and then say highlight. I would like to remove these that had already pre-entered. I want to highlight them and then enter them there. Highlight, enter. You can choose to enter one by one by clicking one and it enters. Then after that, we want to say let us go to statistics. Let our statistics here, usually in these statistics, we want to make sure that these are checked. Whatever you want to be displayed in your output report, then you have to check it. I'm checking R-squared change and descriptives. I'm also checking the confidence level. We are setting our confidence level that we are confident 95%, so we expect 5% error. When we expect 5% error, we shall have set our alpha value to be 0.05. That is the 5%, which is 5 out of 100, the 0.05, the alpha value. So we have already set our alpha value. Then now we can say continue. We can also set our plots. For example, if you want to make sure you have in your files, you have what we call a histogram, and also you need to have the normal probability plot or that normal probability distribution, the curve. You can also say continue under plots. Then after that, we are good to go and click OK. Now, we can now see that our data has been displayed. Our descriptive statistics here indicate that risk scores, these descriptive statistics, are the measures of mean and standard deviation, and n is our sample size. Our sample size is 10 because we are looking at 10 respondents in here. If you counted how many are here from 2 to 11, those are 10 respondents. That counts to our sample size that SPSS is calling the sample size here of 10. And then the mean means the average of all. The average scores means the total scores divided by the number of respondents, which is 10. So summation of n for scores divided by number of n when counted with what we see here as mean. So it mean also in ordinary language means average. So if one was to look at here is to say, let me get the average of the risk scores. We will see that the average of the risk scores will be 5.3, which SPSS is showing for us. And also average age is the total age of all divided by 10. And then you will see that that is 49.3. So that is the descriptive statistics you're seeing here. And also for the others, you're seeing that descriptive statistics. Those are averages. We cannot base on averages to conclude and draw a conclusion about our hypothesis and about the strength of our variables, but they can describe the characteristics of our data. However, we are also seeing here the alternative called standard deviation. Standard deviation means how far are the values from the mean. The more spread the values are from the mean, the wider are the scattered. That's how scattered data is. So we here this tells us that 2.4, okay, almost 2.9 is the distance from the mean to the biggest value, and also is the distance from the mean to the lowest value. So if you were to say, for example, what is 5.3 minus 2.5, you would fall around the 2.8. 2.8. That means that the almost the least value is 2 or close to 2, and the maximum value would be almost 9, which is actually how our data is spreading here. So it is 9 away from the mean of almost 5. So the distance is 2 point. The distance between the mean and the values is averagely it is the standard deviation, which we are seeing here as 2.5. So the standard deviation for each of the values is that displayed in there. And therefore, here when we are coming to analyze our data and making sure we interpret our data, we also look at what we call the model summary. The model summary will give us how strong, what is the contribution of all the variables to the dependent variable called risk score. We see that now the values for interpreting R here, which is 0.983, we saw that already when we are studying the spreadsheet, running regression analysis in the spreadsheet. But our interpretation was here. I just want to borrow our interpretation here, where we say that if the value of R is 0.01 to 0.44, then we say it is a weak positive correlation. Then if it is 0.45 to 0.69, then we say it is a moderate positive correlation. Then if it is above 0.69, then it is 0.70 to 0.84, then it is a strong positive correlation. However, when it is above 0.05 to 1, which is the maximum probability space that we have, then we say that that is a very strong positive correlation. So predictor, when we are predicting the strength of the variable in general terms, we can base on R here and say this is a strong positive correlation. This R, the multiple R we got in Excel here, is actually the R here we are seeing in our model because we are basing on the very data. However, when we want to see how much does all these other variables contribute to the dependent variable, then we interpret the R squared. R squared is the square of R. However, this square is translated into percentages, and so it means that it is at 96.5%, which is also telling us that it is a strong positive correlation at 96.5%. We shall see later these are degrees of freedom and degrees of freedom 2, and then the significance change. Let us look at what we call the p-values. P-values are the significant levels. These are levels of significance, and we can read them under coefficients. So these significant levels are called p-values. However, you will also see that when we ran the same data in our spreadsheet, and these were also called p-values in spreadsheet. So p-values are also called significant levels of significance. Now that we are basing in SPSS, but not to get confused with the language, significance levels here are called also p-values for specific variables. For age of respondents, you can see that the p-value, which is the level of significance, is 0.96. Now, how do we make decisions to determine whether this is significant or not significant? Now, we set our alpha value. The alpha value that we set was the error, which was 5%. The error we set is also called the alpha value. The alpha value that you set for our case is 0.05. That now determines for us what do we call significant and what do we call not significant. When the alpha value is below 0.05, we say that that is significant. However, when the alpha value, when this p-value here, when the p-value here is below 0.5%, this is below 0.05. It is below 0.05. Maybe to repeat for you is that we have set our alpha value, which is the error, at 5% for us to have 95% confidence. So this alpha value of 5% in decimals, it is 0.05. We call it the alpha value. So to interpret this column of level of significance for each of the variables here, for example, age, we base on the alpha value that we set. When we set our alpha value at 0.05, and therefore when we read here our p-value, and we find that the p-value we are reading here is greater than 0.05, then we say that the relationship is not significant. However, when we find that the p-value, which we are also calling significance level, this, like for example here we have 0.096. This one we compare it to 0.05, which is the alpha value. So we say that this p-value 0.096 is greater than 0.05, which we set as our standard alpha value. So we conclude and say that this relationship is not very significant. So it is not significant. Why? Because the 0.096 is greater than the 0.05 alpha value. However, if we had here a figure which is below 0.05, then we would say accept that this relationship is significant. Therefore, we would say age of respondents significantly contributes to the risk scores. But this one we cannot state that. And then we also see that level of cholesterol, this is blood pressure, is at 0.305, which is far above the, it's almost 30.5%, which is far above the set alpha value of 0.05, which is 5%. The alpha value we set is 5%. So this is at 30.5%, which is far away. So they say it is not significant. So blood pressure, it does not significantly contribute to the risk scores. Then we also say that the cholesterol level is also now above the 0.05. So it's greater than the alpha value of 0.05. So because it is greater, then we also say that cholesterol levels do not actually significantly contribute to risk scores. That is now for each independent variable. Now, again, this total here, 0.03, is for all overall p-value. The overall p-value. The overall p-value is 0.03, which is less than the 0.05. So overall is significant, but these individual dependent variables, then we can also interpret them. We can also see here our t-values. Interpreting our t-values, we shall set another session and another tutorial to interpret our t-values, where we shall base on the t-tables to interpret the t-values using the degrees of freedom. However, you could also see that our unstandardized beta values are the total unstandardized beta value is -10, which happens when the x value is at 0. And then remember that this is a linear regression which bases on a line. And to interpret this very well, we did that in our Excel sheet. Where we said that we have alpha naught, others also call it beta naught, which is the coefficient beta naught. Remember, these ones are called coefficients. In SPSS calls them unstandardized values of beta. So they are the ones that we use to actually predetermine or predict the dependent variable when we know the independent variables. So how did we do it? We use an equation of alpha naught plus beta 1, which is age, x. We can know that age, the specific age, which is x. Then beta 2 is the pressure. Beta 2 is the pressure. times age of times the pressure, which if we have known the pressure of the person, then we can also multiply it. Then beta 3 is now the beta 3 times x. If we know the cholesterol levels specific for that person or that patient, then we can also determine the level of risks. So that is what we actually did. For example, to know a person who is aged 58 here, 58, we can predict if a person is aged 58 and also has cholesterol levels 55 and also has uh, uh, the cholesterol level, has blood pressure 155, has cholesterol levels 240, and then now we can base on the alpha or on the beta values here, which are coefficients. So we say this 10 plus, this is the alpha or beta naught, plus beta 1 times x, beta 1, which is the 0.29, 0.29 times the age, which is 58, plus blood pressure. We go to blood pressure. The constant or the coefficient is 0.035 times the blood pressure. That person is at blood pressure, which we are calling 155 times 155. That will be beta 2 times the x, which is 155 here. Then we come and say, what of cholesterol? The coefficient, which is the unstandardized beta, is 0.02 times the x specifically the variable is 240, so that we can determine what will be the risk scores. Risk score. Now we can be able now to tell that the risk score will be 7, which is also there, 7. So if we know the coefficients, the beta naught or alpha naught, the beta naught there, and add a multiplication of the betas values and their corresponding variables, we can predict what actually happens to the risk score, to the dependent variables. So you can get the dependent variables from the independent variables. When we know the independent variables, we can easily predict the dependent variable. This is exactly the story that is here in these coefficients. You realize that these coefficients are not any different from the coefficients that we got in Excel. We can see that these are unstandardized beta values, so Excel is calling them coefficients. And then this is age of respondents. This age is 0.129. This one is rounding it to 0.13. Then blood pressure is also there, 0.035. This is 0.035, then the decimals. And then cholesterol 0.02, 0.02. So the differences are not there at all, because we are interpreting this data from the very source. We are having the same source of translating data. Now back to our SPSS, we also ran our graph for the histogram. This is the histogram. Remember, we ran our data in analyze. we went to regression. Then after going to regression, we selected linear. After linear, here we selected linear. Then after selecting linear, that's where we went and started to say, let us plot our data but include the histogram. That's how we went to include histogram and also the normal probability plots. So when we did that, that's why our data here is coming with the histogram, is also having our normal distribution plot, our distribution plot. So usually the histogram comes with that U-shaped or bell-shaped curve. So then this is our scatter graph, giving us a representation of how the risk scores are faring, basing on the expected cumulative probability and the observed cumulative probabilities. So this data gives us a real summary of what we have run in our SPSS. So in summary, we've seen how to enter data in our SPSS. Or to enter data in our SPSS, we said that you need to first look at when you open your SPSS, you need to first look at specifically the column called this sheet called the variable view. So we then populated our data in the variable view, but each column name contributes to the columns in data view. Then we can type our data in each of the rows and columns, and then, or if data is already available in this existing in the spreadsheet, you can copy it and paste it accordingly. Pressing it very precisely is very key, because validity and reliability of data has got to be maintained as data quality control measures in research. So then after that, what we did was to come and analyze, to run regression analysis. We came to analyze, ran regression, went to linear. After running to linear, we selected our risk score and pushed it here as our dependent variables and highlighted all these to be our, pushed them to be our independent variables, and then set our statistics to have estimates, to have confidence levels 95%, the model fit, and also the R square, and we also checked the descriptives to display. When we said continue, we also said let us have some plots of data where we have the histogram, we also have the normal distribution probability plot. So then, but we did not allow our data to have the Z scores and also the residuals data. So we just had to say continue and said okay. Then from that, that's where we got our ANOVA tables. Now we can save our tables. To save this, you can say print. You can just to print it as a PDF. My printer here is PDF, so I can print a PDF and call this trial version. This is tutorial 31. I can even name it to be SPSS tutorial 31 online. So when I've saved it, and I can now get it from there, but doesn't mean that you have saved your file here in SPSS. So now you can also save the output. To save this output file in SPSS so that you can retrieve it, you also say here file, save as, can save it as my output version 2. I save it also there. Then also this raw data in SPSS, this that I've entered here, I can also retrieve it by saving the SPSS data as the input data. That's input, the other one, the report, is the output. Can save it as version 2. I've saved. So thank you for being there with us and then following all through. Remember to subscribe our YouTube channel. Subscribe, like, and share. The wisdom will spread to everyone. My name is Wilber Ssebuyungo Kivekayunga. I'm a lecturer at Nkumba University and also following up through Clark International University of Kampala, and that is Clark International University with my MBA. Those people have done me good in the MBA business, a master's in business administration. Nkumba University has also done me well with a doctorate in education planning and management with specialties and concentrations in artificial intelligence and digital transition for expanding the digital space. So thank you. We offer consultancy services in organizations. We also make sure that we do planning and management. We also educate communities around the world. In the international developments, we are mainly propelling what we call digital transformation and also the green transition, where we are looking at decarbonization to achieve the zero carbon levels in the world. So thank you for being with us. For emails, you can now email us here, and also on our contact telephones are also displayed there. Thank you for following. Have a nice time.